All right, have any questions? No questions? All right, there's something, one topic I neglected on chapter 19 was coupled reactions. And let me talk about that right now. You know, the typical ways of altering driving force, delta G, are temperature and concentration and pressure changes, right? Does a catalyst alter delta G? This is a good question. Does a catalyst alter delta G? No, it doesn't. It'll make the reaction go faster, but it won't change. That's because the catalyst changes the path, but delta G is a state function. Delta G only depends on the final and the initial. And so the path, you know, can be changed between those. The kinetics happens in going from initial to final. You know, the final, it could be, this is exothermic, so here we could have a delta G, actually, if we plot this in G, you know, here we have delta G decrease, which is favorable, right? We want delta G to be negative for spontaneous process. But the same thing can happen here, you know, you have something like this, where here's a delta G that's positive, the final state's up here. But, you know, this barrier, the hump, is what actually, this is what makes things metastable. You know, there's a cliff here, but you know, there's a fence here at the edge of the cliff. The fence is something you have to hop over in order to go off the cliff here. And so this is metastable because there is something that protects you from falling off. If there was nothing that, let's say the energy barrier here was so small, then it just spontaneously react rapidly. There are reactions of this sort where you just mix them together and, you know, the activation energy is so small it just starts to react. We usually call those like pyrophoric. Have you ever heard of pyrophoric materials? Pyrophoric. I used to work with a lot of pyrophoric materials. Pyrophoric materials are spectacular because immediately when they come into contact with air, it ignites into a big flame. You don't need any ignition source. You don't need any hot surface. It just ignites. Okay? Usually with pyrophoric materials, you have to do those using special techniques. This is just, you exclude air. You usually exclude air and water from those reactions. And yeah, the different ways you do it. You know, there's the low budget ways you could do it, and you probably do it in you just get a container, $1 plus. A low budget way, you know, the cheap way is you would get some kind of rubber septum, they call it. You put a rubber septum in here, you poke a needle into it, and then you just start flushing. You poke two needles, one for an outlet, one for an inlet. And so you poke one needle in there and start flushing it with argon or nitrogen or whatever gas you want. And what that does, argon's good because argon's more dense than air. And so what happens is you poke a needle in here, the argon blankets this, and then pushes the air out of the flask. And so you flush it until you're sure that you flushed all the air out, and then you pull out the needles. And then you have an air-free environment in the flask. And then if you want to transfer reagent here, you usually have another flask like this, and you stick a syringe in there with a really long needle. And then you pull out the liquid out here, and then you transfer it over to this one, and you poke it in, and then you squeeze it in. And it takes some skill to do this, right? Or some practice. You know, that's how you develop the skill, is just practice. And so it turns out, unfortunately, at UCLA, somebody was doing that, you know, and one, they were using too much usually you don't want to fill the syringe more than like halfway. That gives you some buffer, and then you can just pull in some argon or something in there too, right? But apparently the syringe that they were filling was just at max capacity, and so when they pulled it out, it started to leak. And when it leaks out of the needle, it's going to catch on fire immediately, right? And it caught on fire, and then apparently they were wearing flammable clothing and suffered severe burns. But you might have heard about that. Did you hear about that? It resulted in a death. A recent graduate. This is stuff I was doing as an undergrad all the time. But apparently this person hadn't had any practice doing it. Well, anyway, it changed things. Now at UCLA, everybody is required to wear a lab coat, as an extra fire buffer. Have to wear gloves. Hair has to be pulled back. Lab has gotten very strict there, and the same thing here. We're thinking maybe we should follow the exact same guidelines as the UCs do, but there's people who don't want to go that extreme. So, additional cost, whatever else. But it's something you should think about. Your personal lab safety, always. This is why you can't always rely. You can't always rely on people telling you what to do, because one of the findings was, this was not enough instruction, not enough step-by-step instruction. But ultimately, you're going to be responsible for your own safety. And so, if there's not enough step-by-step instruction, then you should do something to fix that. Well, anyway. The professor was actually, what was he, arrested? Yeah. A criminal case was filed. A bunch of stuff, yeah.
What happened? What happened?
They settled. I think they settled. I forgot what exactly happened, but it turned out to be a whole big thing.
But he didn't go to jail or anything?
I think he did go to jail, yeah, for a little bit. I'm not sure. You could look it up. It's in the LA Times, in the stories. But it's a big thing, and you can see how dangerous chemistry can be. For sure. I've seen it, people mixing strong reducers with strong oxidizers, and that kind of stuff. Well, coupled reactions, this is a reaction that doesn't want to go. An example of this is something like copper 2 oxide solid. If we want to convert copper 2 oxide into copper metal plus oxygen gas, delta G for this is greater than 0, which means it's non-spontaneous under standard conditions. So if I have some copper 2 oxide, how can I convert that into copper metal? Well, there are different ways you could do that. We could try, maybe we could try temperature. Do you think temperature would work for something like this? Let's see. All right, what would the delta H for this be? Actually, I forgot my book. Can somebody look up the delta H of formation? Actually, it should be there for copper 2 oxide in Appendix D. Because if you reverse this reaction, what is this reaction? This is a formation reaction. Formation of copper 2 oxide from the elements in their standard state. I'm sorry, can you repeat that? Delta H is negative, so that means I have to change the sign to positive here because it's reactants. These are 0, 0, minus a minus, and so it's 1, 5, 7.3 kilojoules for the reaction is written. And so delta H, that's not favorable. Delta S, we'll calculate that. Take the entropy of the products minus the entropy of the reactants. So what is the entropy of copper solid? You know, the entropy should be fairly low. You know, in the tens, in the hundreds, in the several hundreds. What should the entropy be? In the tens. And what is the entropy of copper solid? 33.15 joules per Kelvin. Okay, minus the entropy of the reactants. What? Oh, oops. Oh, that's a product. Plus the entropy of O2. What is the entropy of O2? Is it 0? Entropy of O2? No, it's not. 200. But we only have half a mole. And so rather than having, you know, a mole of gas at 298 in 1 atmosphere occupies what volume? If we have a mole of O2 at room temperature in 1 atmosphere, what's the volume? No, a full mole. What is a full mole? 24.5 liters. And so that would be about half of that. But anyway, since we have half a mole, we expect half the entropy, which is this entropy is called positional entropy, right? Positional entropy is different than, what are the two types of entropy we have? We have positional entropy and we have this is one of those questions that, you know, I didn't speak about specifically, but it's one of those questions that if you've gone through this enough times, like over and over, then it'll click, right? You'll go, oh yeah, you know, because I was talking delta H is a measure of what kind of entropy? Delta H is a measure of what kind of entropy? If a reaction is exothermic, it dumps heat into the surroundings. Is heat a low entropy or a higher entropy form of energy? Higher entropy, right? Chemical potential is a lower energy, more ordered form of energy is chemical potential energy. And so, you know, this term tells us about the, you know, the entropy, the energy entropy. And delta S tells us about the, what we call the positional entropy. You know, positional, because if you go back to Boltzmann's, you know, when you look at Boltzmann's equation for entropy, what is it? The entropy is equal to K ln W. W is the number of ways you can arrange the different particles. And the more ways you can arrange it, the higher the entropy, the fewer ways. We call that positional entropy because it depends on what the position is. And so when we have a half a mole of gas at, 12 1/4 liters, right? Half a mole of gas, 12 1/4 liters versus 24 1/2 liters, you know, there's a lot more positional entropy in 24 1/2 liters of gas, right? And then you got a lot more particles as well. And so the positional entropy should be an extensive property. It depends on the amount. And then what was the entropy of O2? 205.1 joules per Kelvin. And the entropy of this is, you know, we expected this to be what, on the order of 200 plus, right? Is this typical for gases? So, this one, what do you expect? A higher entropy than Cu or lower entropy than Cu? A higher entropy than Cu. And so what is the entropy of this one? What is it? 25? 0.35? 0.357? Oh, 135. Okay, sorry. 135.7. Which is, you know, when you consider 135 for a solid, is that fairly high? Yeah, that's fairly high. You know, there are these outliers. You know, when I'm giving you these ranges, 0 to 100 for solids, 100 to 200, you know, those are just broad kind of averages, right? But if you're thinking about water, you know, water, would you expect water to be a more ordered than a typical liquid or less ordered than a typical liquid? More ordered than a typical liquid. It should be more ordered than a typical liquid because of strong hydrogen bonding interactions. And so the entropy of water is in the tens rather than in the hundreds, right? In fact, there's something called Troughton's law. Have you ever heard of Troughton's law? Troughton's law just says that the delta S of vaporization, and going from a liquid to a gas, all gases are kind of similar because when you're thinking about positional entropy, there's going to be some depending on the molecule, but most of the positional entropy is going to come from translations in three-dimensional space, you know, the x, y, z coordinates. Right. A little bit from vibrations, a little bit from rotation. And so most gases have very similar entropies, right? Some a little bit higher, but not much. We saw an NO2 versus NO. Do you remember that one? I showed that in class. The entropies were very close, except which one was slightly higher? NO2, but was it higher by much? No, it's like 5 or 6 or something like that. It was barely higher. But you would expect to be a little higher because it's 3 atoms versus 2 atoms. And so you're going to have more entropy there. But, you know, there's something called Troughton's law which says that the entropy of vaporization for most liquids is around 87, 88 joules. And so when you vaporize a liquid to a gas, it's around 87. A lot of, you know, that's just an average and there's a spread there, but a lot of liquids behave like that, but water doesn't. You know, water is going to have a bigger, you know, because of the ordering in the liquid phase. And so there's always going to be those exceptions. Troughton's law, you know, I skipped that entirely because it's not that useful for us right now. It's just if you don't have the delta S. Troughton's law is primarily used when you're trying to guesstimate the boiling point. You can guesstimate the boiling point by solving T. There's a homework problem. All right, so let's figure out what delta S is. What is delta S? Oh, you gave me the wrong value? All right. What is CuO? Yeah, I was thinking that's really high for CuO. CuO is very simple because it's just oxide and copper ion. 42.63. 42.63. All right, that sounds more like it. Thank you. So what does it come out to?
93.07.
What is it?
93.07.
93.07 joules per Kelvin. You know, this is good. Entropy is increasing, but enthalpy is increasing too. So this is bad, this is good. And so what we can do is we can make the entropy term more dominant by changing the temperature. We also need delta G. So this delta G is so easy, though. You know what this is? This is just the negative of the delta G of formation for CuO. What is the delta G of formation for CuO, since we're on that in Appendix D? Negative 129.7, so this would be positive 129.7 since it's just a reverse reaction. Do you guys remember Hess's law? Hess's law says if you reverse the reaction, you change the sign on the energy. So this is it. So anyway, delta G, this is highly unfavorable, right? Highly unfavorable because plus 129.7 pretty much says what? Plus 129.7, what was the kind of the range? Plus 50 to minus 50. So anything over plus 50 is close to no reaction. You know, just barely reacts. Well, maybe there's going to be a tiny bit of copper and oxygen, but it's not really going to happen. But maybe we can alter this to make this happen because if you have a copper, let's say you have a copper penny. You know, a lot of things what people do with a copper penny, if they got some black coating on it like this, is they'll put acid on there. But acid, what that is, you know, if you use acid to clean your penny, what are you doing? What kind of reaction are you doing? It's not an oxidation. The black coating is CuO or Cu2O. Cu2O is more brown. Let's say you got a deep black coating on your penny. It's been heavily oxidized, right? If you use acid to clean the coating, you know, because the copper is going to be coated, so you have underlying copper metal here, and the copper is going to have a coating of oxide on top of it. And so we want to get rid of this oxide coating here. So one way to get rid of that coating is just to react it away. CuO solid plus something like HCl, or actually people use, you could use like taco sauce for this. Acetic acid, vinegar. You put 2 acetic acids, you're going to get what? Two acetates plus water. Driving force is stronger to weaker acid. So this is an acid-base reaction, or double replacement, or metathesis. But the problem with doing this is that you're going to lose copper metal, because where's the copper 2 acetate going to go? It's going to go into the solution. You're going to wash it away. And so a lot of people don't like this because their pennies are going to be even lighter with less copper metal. Whereas this reaction's good because do we lose any copper metal? No, we aren't going to wash it away. All the copper metal is going to be there. We're going to lose it. But unfortunately, this reaction's not going to go. And so how can we make this reaction go? We could try to change the temperature. It looks like we can, right? Because by increasing the temperature, we can make the entropy more dominant. Sometimes we can't, though. You know, if this are negative, sometimes we can't get the temperature. If this were negative, can we get the temperature, the Kelvin temperature, negative to cancel out negative and negative? No, so it doesn't work. And so it should work in this case, so let's go ahead and do that. Well, we want delta G naught, you know, under standard conditions equals 0, is equal to delta H naught minus 2 delta S naught. And so solving for temperature is just delta H naught over delta S naught, which is going to be 157, I'll just convert it into joules, 157,300 joules divided by 93.07 joules per Kelvin, which gives us a temperature of what is it? 1690. That's it?
Point 1213
All right. Kelvin?
Kelvin.
1690 Kelvin. 1690 Kelvin. How are we going to get that temperature? Is that an achievable temperature? What would this be? This would be about 17, so it'd be about 1400 degrees C, roughly. That's an achievable temperature, right? You just throw it in your oven at home. No, you couldn't throw this in your oven at home. You could throw it into a furnace, right? Furnaces can achieve this temperature. The furnace I used to use a platinum furnace. Platinum furnace can go up to about 1600, not to, but close to 1600. And so you can throw this in a platinum furnace. Platinum furnace, though, is very expensive. You can see that achieving this high of temperature is going to be very, very expensive and difficult, right? And this is not going to be so cost effective. But maybe because generating high temperatures is going to cost you a lot of money. And so let's try to do this at room temperature. Is there a way we can do this at room temperature? Well, why don't you do it? Can you do the calculation for me? And tell me how we might be able to do this at room temperature? I go non-standard conditions. Well, we'll go through it this is so hot in here. I don't want to spend any more time waiting. Let's just go through it and somebody tell me what to do. What equation should I write, or what should I do right now? If I want to do this under non-standard conditions, what delta G is equal to delta G naught plus RT ln Q. And delta G is going to equal, we want it, right now delta G is, because right now we're under standard conditions. If we're under standard conditions, tell me what Q is equal to. Yeah, under standard conditions, let's say I didn't change any conditions. We're under standard conditions, we're at 298. What is Q equal to? Q, no. This Q is equal to, give me the number. I didn't change anything. I just want to use this equation. Right now, we're under standard conditions. If we're under standard conditions, what is Q equal to? Not 0.5. 1. Right? Standard conditions, all activities are 1. Therefore, Q is equal to 1. So if Q is equal to 1, ln of 1 is 0, and that means delta G is equal to delta G naught, which is, we're under standard conditions, right? And so this equation is fine for that. Do you see? But now we want to go under non-standard conditions. And so right now, delta G is equal to delta G naught, which is not favorable. It's 129.7 kilojoules. It's highly unfavorable, right? And so what we need to do is we need to cancel this 129. This is 129.7 kilojoules of, I guess you could say, anti-driving force, you know. It's preventing this reaction from going. And so we got to cancel that out by using this term. Because what we want to do is we want to do plus 129.7 minus 129.7, and then we've gotten over this barrier. In order to do that, we've got to set delta G equal to 0. If we set delta G equal to 0, that's equal to delta G naught plus RT ln a Q, right? All right, now what? Yeah, now we want to do this. We want to do that. Delta G naught is equal to, actually, we'll just do this. Delta G naught is equal to delta H naught minus T delta S naught, which is equal to minus RT ln Q. And then we solve for T. T is going to equal delta H naught delta S naught plus minus R ln of K, because when we set it delta G equal to 0. So does this equation look familiar? Is that right? Yeah, but am I going in the right direction? Is this the right direction? No, I mean, this is the equation we ended up with yesterday at the end, right? We don't want to do this. What do we want to do? We want to find K. Because if delta G is equal to 0, this is just equal to K here. And therefore, delta G naught is equal to minus RT ln of K. K is equal to delta G naught divided by RT e to the minus. Is this right? Is this the right direction? Yeah? Yeah, because right now, what did I say? We want to do this at room temperature under non-standard conditions. But if I'm under non-standard conditions, wait a minute, this delta G naught is under, this is standard conditions. Is it okay to use this delta G under standard conditions when I clearly want non-standard conditions? Is that okay to use? In other words, is delta G standard valid when I'm dealing with non-standard conditions? Yes, that's good. That's the kind of answer I would like to hear. Confident, yes. Of course it is, right? Because this equation under non-standard conditions is comparing the standard and adding the correction to that. And so we need it under standard conditions because that's how we correct it. And so yes, even though that this is under standard here, this should be okay. And the temperature is okay because the temperature is 298. And so at 298, and reaction becomes spontaneous. Under standard conditions, it certainly can. Yes, the answer is yes if we go non-standard. Well, let's see if that's really the case. Let me put yes in there. And so K, what is K equal to in that reaction? K is equal to the activity of the product. So we got CO2, or no, we don't. What do we have? We have the activity of Cu, solid, times the activity of O2 to the 1/2. Was it to the 1/2? divided by the activity of CuO solid. Well, the activity of Cu is, and the activity of O2 is just the partial pressure. So this is the partial pressure of O2 to the 1/2. So let's plug this in. The K, which is going to equal the partial pressure of O2 to the 1/2, is equal to E to the minus delta G naught. Delta G naught was a plus 1. I just erased it. What was it? 129.7. All right, so this is 129,700 joules. Divided by R, 8.3145 joules per Kelvin, divided by T. T we're leaving at 298 Kelvin. So that's okay. So we want to solve for pressure. So the pressure of O2 is equal to the square root of this, which is equal to, oh no, actually I got a square, sorry. The pressure of, we need to square both sides, so it's going to be the square of whatever we get here. Which is equal to what? What is the pressure that I need to?
I got 3.4 times 10 to the negative 46.
3.4 times 10 to the negative 46 bars, which is about an atmosphere. Is that what other people got? We could double check this by plugging it back in. But let's see. Yes? All right. So all we need to do is we need to get a container and then hook up a vacuum pump and then pump it down until we achieve a vacuum of 3.4 times 10 to the minus 46 atmospheres, roughly. What do you think? Is that pressure going to be achievable? No. Yeah, 10 to the minus 46 atmospheres. I don't think so. So this is not, I don't think we're going to get this to go spontaneously at room temperature. It would be nice to recover all your copper and your copper penny this way, but it's not going to be very practical. And so what you got to do is, what's the best vacuum that we have in-house here? Well, we have our house vacuum. Our house vacuum is about what? We'll just say half an atmosphere to be generous. But it's probably a lot less than that. I mean, you know, when I say less vacuum, I mean a lot weaker. And so a lot weaker means it's closer to atmospheric pressure, because you need a pressure imbalance, right, to create a vacuum. And so, well, probably the best thing is, since this isn't going to happen at room temperature, what we can do is maybe we don't have to buy an expensive furnace, like a platinum furnace. You know, platinum furnaces, and I've talked about this a bunch of times, right? Platinum furnace. I think that, have I talked about this a bunch of times? Probably, you know, we used to have lots of platinum and gold in our lab, because gold is fairly unreactive, so you have like a bowl, you know, like a cooking bowl. If you want to cook something, right, you don't want it to react, right? So we had gold and platinum boats, they call it, and you scoop up your chemicals in there and throw it in the platinum furnace and heat it up and get it to react. But it's very expensive. It was very expensive back then, but gold's gone up like thousands of percent since then. It was way more expensive, probably cost prohibitive now. People are probably just using ceramic. The problem with ceramic boats is sometimes they start to react with their chemicals. Especially at very high temperature. So what we'll do is we'll do a combination. We don't have to buy this, we don't have to invent a new vacuum system for this. I don't even know what is the vacuum in deep space. Does somebody know? Yeah, we don't have to send out this to space, and then heat it up out there. And we don't have to buy a fancy platinum furnace. Maybe we could do this using our house vacuum and just the regular furnace. Do you think? And so, what temperature would be required at an atmosphere? So, this is the next problem. At what temp would delta G go to 0 at PO2 of 0.5 bar? I was thinking, one of the reasons why our pressure might have been, our temperature for water, you remember we did that water calculation yesterday, it came at 370? I was wondering, maybe it was because I wasn't using bar, I wonder, what is the boiling point of water at 1 bar rather than 1 atmosphere? Yeah, it's like 1.05 or something, right? But times, well, anyway, it doesn't matter. Let's just do this. It was close. This is where we use that fancy equation, right? Do you remember this fancy equation? T is equal to delta H naught over delta S naught minus R ln of K. Here's where we use that fancy equation. And so if we have a half a bar, when we'll plug in our delta H naught, or delta S naught, we have minus R, we have that. ln of K. K is going to equal 0.5 to the 1/2 R. The 1/2 comes from the coefficient. It's 1/2O2. And so this is G raised to the little g divided by A raised to little a. Well, A raised to little a is 1 to the 1. This is going back to chapter 15. I know it's been a while since we've had coefficients. All 16 and 17, the coefficients were always 1. And so the equilibrium constant always was raised to the first. But now we got to think about the others. So does somebody have the answer? Basically, this is what we're doing. We're just reviewing the basic calculations of chapter 19. These are the standard calculations. The delta G from delta G of formation, delta G from delta H and delta S, right? Changing delta G using temperature, changing delta G using non-standard conditions at 298, and now we're going non-standard at temperatures other than 298, right? And so we're getting the full spectrum of calculations. There's, small variations to this. The basic calculations is the same. Does somebody have the temperature? What is it? 1639.1. What was the other temperature? Oh, yeah. That vacuum really helped us a great deal, did it? It did. I mean, we don't have to go, we could go 50 degrees cooler, right? 50 Kelvin cooler. That's helpful, because that'll save you energy, right? It'll save you cost. But it wasn't the great solution. Maybe with a better vacuum, that would help a lot, right? If we could pump down to a milli atmosphere or millibar, at least 1 millibar is actually easy to achieve. Or microbar. Then the temperature should be a lot lower, but not hugely so. And so out of all these options are very expensive, right? And can be very challenging technically. And so are we pretty much out of luck? We've exhausted all possibilities in chapter 19? No, we haven't. There's one more option, but we have to sacrifice something. It's a bit of a compromise, because we aren't going to get exactly what we want. We're going to get close to what we want, right? And the last option that we're going to talk about is coupled reactions. Coupled reactions are very common in nature as well. And so the way we do this is we couple this reaction with another reaction. So this reaction is not spontaneous. And so what we want to do is we want to add two reactions, and this reaction has to have a delta G less than minus 129. See, if I can couple this reaction with a positive and this reaction with a negative, what I can do is I can cancel out this, right, and make this whole thing negative. Right? And that will make it spontaneous at room temperature. And so what I got to do is I got to find out what can I couple this reaction with. Well, what I can think of is this. I want something to attack one of these products. But usually I want which product? I want to keep the copper. I don't want to lose 1 micro ounce of copper from my penny. Make sure I recover all of it. And so I want to make my penny bright and shiny again without losing any copper. And so I got to think of something that attacks oxygen. What likes to attack oxygen? It could be a redox, acid-base, or metathesis. But if you think about metathesis, is any metathesis reaction going to attack oxygen? No. And so it's got to be an acid-base. An acid-base like hemoglobin, O2 binds to hemoglobin. Hemoglobin is iron 2 and a heme in blood, right? Is that a very effective? No. Does it bind very tightly? No. And so what would attack oxygen? Give me a chemical that likes oxygen that would attack it. If somebody asks you what are the chemicals or properties of oxygen, well, what does oxygen like to react with? Reducers. Give me a reducer. That's good. Methane was good. Or, what is another good one is hydrogen. If I take hydrogen and react it with half an O2 gas, I'm going to form H2O liquid. Look at this reaction. You recognize this reaction? This is what we call a formation reaction, and therefore delta G for this one is equal to the delta G of formation of H2O liquid. And so what is the delta G of formation of H2O liquid? Someone look that up for me. Minus 237. Okay, so we got plus 129 minus 237. That's going to give us a delta G net of minus 108. Minus 108 kilojoules. 108 minus 108 kilojoules means it's highly spontaneous. This net reaction should be highly spontaneous, and the net reaction is going to be CuO solid plus H2 gas yields Cu solid plus H2O liquid. And so the compromise is here. Rather than forming O2, which is a valuable product, we're going to form water, which is a much less valuable product. Right? And so if you wanted the O2, well, you aren't going to get it. You're going to get water instead. This one I had a demo for, which is very nice, and I'd like to show it. But it's a bit dangerous, this reaction. So I don't want anything bad to happen. But it's quite nice, especially if you heat this up. If you heat this up, it goes even faster. But if you heat it up, you got to watch out for the hydrogen reacting with oxygen and air. Okay, this is an example of a couple of reactions. Couple of reactions, you can see, well, now we can do this under standard conditions at 298 Kelvin, but it's going to cost us. It's going to cost us the price of hydrogen gas, which is probably cheaper than trying to generate huge temperature or huge vacuum or a combination of both. Does that make sense? The other thing is we didn't do, the other thing is concentrations. We haven't dealt with concentrations because the reactions I chose. But you could alter concentrations. Unfortunately, we can't alter concentrations here because we don't have any aqueous solutions. But in the next chapter, we're dealing primarily with aqueous solutions, and we have lots of concentrations, and we're going to change those to see how those impact delta G. All right, so this is kind of a review of 19 plus a couple of reactions, the last thing. Any questions? So let's take a break, and then we're going to start our chapter 20.